Hello, everybody. Today we continue our study of calculus. Hopefully, you will see something kind of beautiful today happen when we evaluate some of these derivatives. So, just in case you didn't know, calculus was not just Isaac Newton or Leibniz who created it. They stood on the shoulders of giants, so to say, in that mathematical knowledge had to build up and build up and build up to get to the point where Newton and Leibniz could just, kind of define it as its own subject of calculus. Right? Calculus is based upon infinitesimals, meaning studying as something gets really, really small or as something gets really, really big. And just to clarify what that means in terms of what we've been doing, we've been studying the slopes of tangent lines and secant lines, meaning we've been trying to find the equation of a line passing through 2 points on a graph, right? So let's call this x. We've been trying to find what's the slope of this line that passes these two points on the function f of x, right? So we said this is x, therefore the y value is f of x, right? And then we said, okay, well, let's let this be h units over. Let's let the next point be h units over. So it would be x plus h, right? Whatever this is, x plus 3, x plus 4. And therefore, the y coordinate on here would just be plugging in f of x plus h. And then what we said is, oh, well, the slope of this secant line is simply just subtracting f of x plus h minus f of x, and then dividing by x plus h minus x, right? Subtracting the x coordinates. And if you do this, you get f of x plus h minus f of x. The x's cancel out over here, and you're just left with h, right? So that would tell you the slope of this secant line, right? Like you could imagine if you plugged in numbers. But then we end up wanting to know the instantaneous rate of change, which is the slope of a tangent line, right? It's the slope of the line that passes through just one point, like such. That's not a great example, but it looks like that. And so what we would do is we would make this h smaller and smaller, right? We would make this point come closer and closer and closer. And if we get it close enough, if we get infinitesimally small, then this secant line turns into a tangent line. And the way we do that, the way we make it small is we take the limit. Remember we studied limits last time as h goes to 0, right? So we're going to study like what as this value here gets really, really small, right? Then the distance between the 2 points gets small. And so we end up with this, which we'll get into this even more next lesson. But this is a study of infinitesimally small, right? This h value is getting really, really small. And that's what calculus is based upon. And hopefully you'll see as we move through calculus, you'll see how powerful it is. All right, so we're going to start with this, just a quick application of some notation. Remember, we defined f with this little prime symbol above it as, this is called the derivative, right? You should write this down. It's called the derivative of f of x. And what it represents the slope. This is really important to understand this. The slope of the tangent line. Right? So the slope of the tangent line, or the slope of f of x at any x value. Right? So for example, if I said f prime of 2, this would be the slope of f of x at x equals 2. Right? So this again is representing slope of a tangent line at a given point, right? And if I had an x here, then it would be the function for the slope of the tangent line. Okay, so let's do an example just to reinforce this idea. This one here is read as f prime of -7, which means it wants the slope of the tangent line at -7, right? So I would go to -7 x value, and I would look and I would think about this, and I would say, what is the slope, right? What's the rise over run of this line? I'm not actually going to calculate it in this case because this is not a very accurate way to calculate, as you probably noticed. But I would say, what's the slope of that line? What I can say for sure here is that this has negative slope, right? So in case you need a reminder, positive slope looks like this, right? Negative slope looks like this. There's also zero slope, which is straight across. And there's one other kind of slope, which is undefined, which is if you have a vertical, that's undefined slope, right? Because your rise would be a number, but your run is 0. So you might have like 2 over 0, which is undefined, right? So 4 kinds of slope: positive, negative, 0, undefined. At -7, the slope of this function is negative. So I'm going to write that as this. This one is less than 0, right? Less than 0 are negative numbers. If I go to f prime and -4, that's here. right? Imagine if you, what's the slope of this function here, right? Look at it. See how it's real flat? Looks like it goes straight across like this, which is this case, right? It looks like it has 0 slope, right? So I'm going to say this one is probably really close to 0. F prime of 1 is here, right? And we want the slope at that point. You can see the slope of that one would be positive or greater than 0. I'll go ahead and label it as negative, 0, positive. And then F prime of 6 is here, right? And we can see that it's also greater than 0. And what you're being asked to do is order from least to greatest. So obviously, the least one is going to be f of negative 7, right? Because it's negative. And the next one would then be, and this, so this is going to be less than f prime of negative 4, because that one is 0, right? So you go negative 0. Now we look at the positive ones, these two, and we're trying to determine which one has a greater slope. Well, greater slopes are steeper. Hopefully you remember that, right? Greater slopes go up farther than they go over, so they're steeper. And you can see that the slope at 6 is steeper than the slope at 5. So we're going to put, it's not at 5, at 1. So we're going to put f prime of 1. The slope at 1 is less than the slope at 6. And so this is how we might order them from least to greatest, because you're going from negative slope to 0 slope to positive slope, but not that steep, to positive slope that's steeper. All right? So that's part of what I want you to understand. The next part of what I want you to understand is I want us to try to start being able to find a function for f prime of x, right? I actually want you to be able to write, oh, f prime of x is 2x plus 1, right? You have a function that will tell you the slope at any point you want to know. And this is one of the problems that was on the last practice set, but we're going to try to really formalize that process and try to come up with a rule for ourselves. Okay, so we're going to start with let's create a table of values. Let's choose some x values. It doesn't really matter what you choose, but let's choose them in order so we can try to look for a pattern, right? So let's choose negative 2, negative 1, 0, 1, and 2. And what we're over here, what we're going to find is we're going to find f prime of x. The way we're going to find f prime of x is we're going to do it the way we've been doing it, where we're basically going to find the slope of a secant line and make the secant line try to turn into a tangent line, right? And so the way we do that is x to the 4th looks like this. If I wanted the slope at negative 2, that's here, right? So maybe the first thing we do is so this is negative 2. Maybe the first thing we do is we find the slope between negative 3 and negative 2, right? So in order to do that, we would say f of negative 3 minus f of negative 2 over negative 3 minus 2. And this is going to give us an approximation. It's not going to be a great approximation, but it will be decent, right? And then what we do is we'd say, okay, I get that number. That's not going to be very accurate. I'm going to choose a number even closer to negative 2. So I'm going to choose that one, right? And what that one would look like would be f of, let's say the x value there is negative 2.3. I just chose something closer to negative 2. So negative 2.3 minus f of negative 2 over negative 2.3 minus 2. And we'd get an answer here. And this would be a better approximation of the slope at that value. And then we're just going to choose numbers here that are closer and closer to negative 2. So if I wanted to generalize this, I would say f of x minus f of a over x minus a, and where we would take the limit as x approaches a, right? As this number approaches this number, and in this particular case, a is 2. So I'm going to replace this with negative 2. Sorry, it's negative 2. Right, so we're going to do that as x approaches negative 2. And in general, again, it's a, and later on a will take on these values, right? So let me get this set up so you can see. Okay, so I'm going to do this one on the calculator so you can see how it would be done on this calculator. We don't need that. First, we're going to go to y equals, and we're going to put in our function, right? Our function is f of x equals x to the 4th. So I type that in here. Next, I'm going to go to my home screen, and I'm going to do alpha. Actually, sorry, let's do this first. Let's put parentheses, alpha trace, I put it in y1, so we're going to do y1 of, let's do the first case, which is this one, negative 3, y1 of negative 3. We're going to then subtract alpha trace y1 of negative 2, close that parenthesis, and we're going to divide this by negative 3 minus, oops, I need some parentheses down here as well, negative 3 minus negative 2. And I think I forgot to put that here, right? This should be negative 2. We're going to press enter. And so in this case, I would have gotten negative 65 as my the slope of that secant line there, right? So then what I want to do is I want to get closer and closer to negative 2, right? So I end up changing this number. I change it to negative 2.3, the next one. I should insert negative 2.3 minus negative 2. And up here I have negative 2.3. Right? So now I'm just entering this. And again, this should have been a minus negative 2. And we're going to get, if we do this, negative 39.947, right? So again, this would be a better approximation than this one. And then what basically we want to do is we want to make this number closer and closer to negative 2. And you can kind of just jump there. You don't have to do the ones that are far away, right? But just remember, you can't plug in exactly negative 2 because that'll give you 0 in the denominator. So let's plug in negative 2.01. That's very close to negative 2. We're going to plug in the same thing over here. Negative 2.01. And that's going to give me the next one is negative 32.24. So this is when, x is negative 2.01. What we want to do is see what is this number approaching. So we're going to go a little bit even closer. We'll add a couple of zeros in there, and we're finding a limit as this gets closer. So I'm going to add 2 zeros, so 2.001, very, very close. This is indistinguishable to the human eye of whether this is a secant line or a tangent line, and you get negative 32. So would you guess that it would be negative 32? Yes, I think so. So this is negative 32. Right? We're going to do the same thing for x value of 1, which means up here what you need to do is you need to change this value to negative 1, right? And our numbers should all be approaching negative 1. So again, we're just going to get really close to negative 1 right now. We don't have to go through the ones that are far away. Make sure you change all these things to negative 1, and then something really, really close to negative 1 for this one, right? And if you do that, you can see, you could test this out some more, but it looks like it's going to be negative 4, right? And then we're going to do 0, so we go back up, and we do the same thing. We're going to change this to 0. We don't really need negative 0, so we're going to delete that. And then we want this number to be really, really close to 0, so let's go negative 0.001. And again, we want this to be 0, but we don't need the negative. And we want the same thing here that matches the other one. And we're going to get 1e to the negative 12, which hopefully you recognize that's 0.000000000, a bunch of 12 zeros and then 1. So that's effectively 0 if as close as 0 as you possibly want it to be. Then we're going to do 1, right? So same idea. Now you're going to plug in 1 here, not negative 1 but 1, and then this should be really, really close to 1, not negative 1 anymore, but close to 1. And same idea here. This is 1. This is really, really close to 1. And I kind of hope you find this a little bit tedious, because it should be kind of tedious. And you get 4 again. And then maybe you can predict, oh, this is going to be 32. Right? And what we're trying to do is we're trying to write a function for this. Right? What function is going to relate these things here? So I don't know if you see it yet. It's a good chance to practice our modeling skills. So we're going to go to list, edit, and we're going to go ahead and enter these numbers into our list and see if we can fit a function to these points. All right, so I'll pause while I enter my numbers. Okay, so I have my numbers. Hopefully you can tell it's not linear, right? It doesn't have a constant rate of change. It has some negatives, some positives. Exponentials don't have negatives. We might be a little bit confused about what it is. Let's go ahead and graph it just to see what it looks like. We only had x values from negative 2 to 2, so let's just change that. Let's make this 4. And then, our y value's got to go at least down to negative 32, so let's say negative 40, and at least have to go up to positive 32, which is 40. And we'll graph, and it's graphing the original function. We have to go over, it's a good review of some prior stuff, you have to go over the plot, second plot, and then make sure you turn this on. right? And then go to graph. And then you can see it looks like that. You can see it's definitely not linear. It looks like, let me grab it real quick and put it over here so I can see, maybe you can see what it looks like. It looks like it comes up like this, across, and then over. And maybe you recognize what that should be, maybe you don't. So let's look at some of our options. Let's go stat, calculate. Do we think it's linear? No. Do we think it's a parabola like this? No, that's not parabolic. Do we think it's cubic? Do you know what cubic is? Maybe you do, maybe you don't. Quartic, so the cubic would be like something to the third power. Quartic would be something to the fourth power. Then there's linear, exponential, and then there's power regulation, power. So let's try a power model real quick and see what happens, right? Oops, I have to do that again. Calc, power, and yeah, it's not gonna like the. Let me see. It's not gonna like the negatives, I think. So the power reg is not going to work just because it doesn't can't handle the negative situation here. It's only for direct and inverse variation. So maybe you recognize, hey, this is a cubic function because it goes down on the left, up on the right, meaning the degree is odd. So let's just show you if you do calc. You could try some of these. Like so, let's just let's just do cubic, and you'll see that cubics usually are something x to the third, something x to the squared, something x plus d. In this case, a is 4, meaning this number right here is 4. Everything else is 0, and the r squared value is 1, meaning this is perfect correlation. Like this function fits this data perfectly. So if we wanted to write the function for these for the derivative, it would just be the a value of 4. All of these things are 0. So it's going to be 4x to the third, right? So f prime of x is going to be 4x to the third, right? So just we want to write that down. If f of x equals x to the fourth, then f prime of x equals 4x to the third. What that means, if I want to know what's the slope at x equals 10, I can find f prime of 10, and that's basically just 4 times 10 to the third, which is 1,000, 4,000, right? So if I did this procedure I did on my calculator at 10, I should end up with 4,000. So it's an easy way to then find the slope at any point that I want. All right, so you're going to be doing that a lot with different functions and trying to figure out if you can find a connection between, here and here to help you skip some steps. Just a heads up, this work is even though I showed you on our old calculator, it's a lot easier. It's done a lot easier on Desmos. For example, if you just type in, f of, let's say, a minus f of negative 2 over a minus negative 2. And then we got to define f of x. F of x. Okay, let me start over. So then start with f of x equals x to the fourth, your function, right? And then you can write this. So this should be the next thing down. And you just add a slider for a. Then you can just make this a value get closer and closer to this value, and you can see as a approaches negative 2, that's x squared. We wanted x to the fourth. As a approaches, we get really, really close to negative 2. The slope is getting really, really close to negative 32, which is what we had over here. And so, like, if I wanted to check, well, is the slope, did this function work out? Is the slope at 10 actually 4,000? Then I could put 10 here, and I could put 10 here, and then I could choose values really, really close to 10 for my a, right? So like maybe 99.99999. It's close to 10. That's close to 109.999999. And you can see as I get really close to 10, the slope gets really, really close to 4,000. And so we could say, yes, that is, our function is predicting the correct numbers.